Okay, is there a way to look over what we missed on the dry lab? So I'm going to give a blanket answer to that. Is there a way for you to go back and see what you missed on any assignment? Okay, has anybody figured that out? How many of you have that question as well? There is a way. There is. Who knows? Anybody figured it out? So if you check, for example, quizzes, how many of you have been able to see correct answers on quizzes? Go back and see those things. How many of you have not been able to see those? Okay, so if you check the day it's due, like we had the quiz Tuesday, and if you finish your quiz and immediately try to check, no, you cannot see correct answers. But if you wait till the due date is passed, I have specifically selected for all the answers and things to be made available once the due date has passed. And there's a reason for that. Obviously, you could probably understand it would just take one person at 8 a.m. to get on and ace the quiz and then see all the correct answers, and then it's game over, right? Like anybody could, that information could be shared. So the reason I have it set that way is so that it's an honest quiz for everybody. So once you go back, like the next day, like I would love for somebody to go into Blackboard right now and go to where you see your grades, and you can click on the grade. Somebody in the 8 a.m. said it's blue. That's the hardest part for me as an instructor. Sometimes I don't know how things appear to you guys. Like the student interface is different than the instructor interface. If your camera is not working and you have a legit reason for that, that's okay. But otherwise, I really do ask that you turn your cameras on. Maddie, you said, yeah, it is. Yeah, it is to what? Yeah, what is? Sorry, I missed that.
It's blue.
Okay, good. Yeah, it's blue.
Back to see the questions.
Thank you. So you click on that and you should be able to see correct answers. That's very important to me that students can see those. So going back, Matt Curtis, going back to what you were asking, once the due date is passed, so those labs are due Sunday at midnight. So Monday, Tuesday, Wednesday, as you prepare for the exam, you'll be able to see the correct answers and everything for that lab. And I'll try to remember to post a key for the lab as well, so you can see how I work things out. So anyways, that's how it'll be for exams as well. The day after the exam, especially for all the multiple choice stuff now, if it's a question that I'm having to hand grade, like an open response, that'll take a longer time for me to grade, but you should be able to go in and see the correct answer for all the multiple choice the day following the exam. Another question in the chat, are the labs on Mastering or Blackboard? Anybody want to answer that? Blackboard. Labs are always on Blackboard. Homeworks are on Mastering. Do we need to print off the wet lab PDF before going to the wet lab? I've had students do both. Some students love to have it printed off and have a hard copy and you can read through it and write your data down. Some, they've used their phone and pulled up the PDF and they just write their data down on a sheet of blank paper, okay? Now here's the important thing. Some of y'all are gonna be in lab with me this afternoon and tomorrow, I guess. Make sure you have correct clothing, okay? What is correct and acceptable clothing? I really hate when I have to ask students to leave the lab because you've driven here, you've taken the time, some of you drive in from a far away. Please wear closed-toed shoes, pants, and have your safety goggles. No crop tops, okay? No crop tops, no shorts, no open-toed sandals and things like that. So please wear appropriate clothing. And this is fine when it's cool outside, but when it gets warmer, please remember that. And then bring your safety glasses as well. Okay, any other questions? Are the exams open all day or do they have to be completed during our class time? Those will be taken during your lecture time. Okay, so you will log on next Thursday at 10:50 and you will begin the exam and you'll have like 2 hours to do it. I know some of you may have a class you have to go to after the hour, 15 minutes, hour and a half time schedule. So please make sure you feel comfortable at least completing the exam in an hour and 15 minutes. That's all the time you would have if we were in person. Online, I just keep it open for about 2 hours. Okay, I give you some extra time. All right, all great questions, all good stuff. But overall, I hope y'all are feeling okay with this. I know some of y'all have jobs, okay? Some of you work night shifts. I've had students that work night shifts before and you're exhausted during lectures. And some of you are parents and you have children. And so I know you have a lot going on and that's why I want to be approachable. I've had several students get on Zooms with me and we've worked problems and I hope that's been helpful. So please reach out. I'm here to help. Don't just feel like you have to go to the library for tutoring. reach out to me. That's what I'm here for. So do you know how many questions are going to be on the exam yet? Not yet. Usually there's somewhere around 20, but certain parts maybe have like part A, B, C. Usually there's 10 to 12, maybe 15 multiple choice. When are office hours for Zooms? Can anybody answer that? So all this info, off topic, but I love your earrings. Thank you. Thank you very much. So all this info about office hours, when I'm available, how to reach me, it's all on the syllabus. And I'm not saying that to say I don't want to answer your question. I'll answer your question. My office hours are 9:30 to 10:30 on Tuesdays and Thursdays. And then Friday, I've had an issue with doing the Friday Zooms because I've been in lab with students on Fridays. But eventually, once we do the Zoom breakouts and Dr. Dunlap is handling the Friday noon lab section, I will hold my Friday office hour, okay? So all of that's on the very first page of the syllabus. So I'm going to harp on this again. Please, please, please read through the syllabus if you have not yet done that. I know several of you maybe probably have, but if you have not, the reason I say that is because you may have a question, you may email me and I don't get back to my email for an hour or a day. And you need that question answered. And so that's why I've tried to put all that info in the syllabus so you're not waiting on me sometimes and that information is accessible to you. So, all right. Well, we're going to get into, 10 minutes in. So we're going to get into lecture, ionic compounds, okay? Make sure you have those slides and, there we go. Okay, let me get the chat up. There we go. Okay. So ionic compounds, chapter 3. So exam 1 is going to cover all of this stuff that we've gone over so far. All right, new picture here. This is the last picture from the Grand Canyon. I'd love to know, has anybody been to the Grand Canyon? Anybody love to do hiking? Anybody just despise the outdoors in general? Somebody this morning was like, yeah, I don't like bugs. I've been there. Good. So if you go to the Grand Canyon, again, this last picture, the next pictures will be closer to Arkansas. You can go see Horseshoe Bend. Okay. So it's a little bit of a drive depending on where you camp and where you stay. But we drove here and it's kind of bizarre because you can't see Horseshoe Bend from the road. So you feel like you're in the wrong spot. You're like, I don't see anything massive. It's like a big sand dune. You got to park and then you walk over the sand dune and then boom, it's there. You see it. It's awesome. The scary thing about this is that there's no railing. You can literally walk up to the very edge of the canyon and just plop your feet down and dangle them over the side, and that freaks me out. So I did not get that close. And you just need to be careful if you go. But this is one of the most iconic places in the world for some photographers. You have to have really special lenses to get everything. You can see there's parts of the picture that are very cut off because my camera lens just wasn't big enough to get all of it from where I was standing. So anyways, obviously you can tell why it's called Horseshoe Bend because of the way the water flows around the canyon in this part, but really beautiful, really cool place to stop and see. And anyways, that's Horseshoe Bend. So let's talk about chemistry now. Recap really quick. Tuesday, where did we finish off? Tuesday, we talked about the periodic table, how it's organized, and then we talked about valence electrons. We talked about how to count them, and we said that's going to be really important for everything we discussed today, and that's the truth. Because we said there's something very, very stable when an atom or an element has how many valence? How many valence electrons is like the special number, and they're yes, 8, okay? So there's a rule we're going to get to later that helps us with that, but that kind of hits on the first blank today is that all atoms within nature, they desire to be in the most stable state possible. Okay, they want stability. And sometimes naturally, inherently, they're just not as stable as they could be if they were in a chemical bond. So that's the reason electrons will be given away or traded, like we talked about at the end of Tuesday, And when electrons are traded, that's where you enter into a chemical bond. Okay, and think about in nature, our bodies, the things we eat, the things we breathe, the elements we come into contact with, usually they're in compound form. And compounds are held together. They're atoms and elements that are held together by chemical bonds. So what is a bond? They're a direct result between the electrical attraction of opposite charges. Okay, the electrical attraction of opposite charges. So I've got this cute little picture here, right, of the proton and the electron holding hands, and that's the chemical bond. Okay, remember that the electron of every electron in every atom is attracted to the nucleus where the protons are. But the closer atoms get to one another, the electrons from one atom may also begin to feel the pull of the nucleus from the opposite atom. I'll show you an example. So like there could be an electrical attraction between the nucleus of this atom on the right and the electron of the atom on the left, okay? And that attraction will pull that electron. And remember, some atoms are very happy to give away their electrons anyway, so it doesn't take much persuasion for an electron to jump ship for some elements, okay? Now, I want to ask you guys, what elements do we have? This picture down here is a little more technical. I want to know, what elements are these? Remember, we have the nucleus in the middle and the energy shells, 1 and 2 layers, 3 layers, 4 layers, depending on what row the element's in. How do we know what elements these are? You can figure that out. Remember, we identify elements by the number of protons in the nucleus, and all elements, before they enter into a chemical bond or trade electrons, they have an equal number of electrons and protons, okay? So the number of protons is going to be equal to the number of electrons in any atom starting off. So how many electrons do we see over here for this element, this picture on the left, the atom on the left? See these black dots right here, these are the electrons. So you see 3. Okay, Keegan, so what element would this be? If there's 3 electrons, there's 3 protons, so it is, if you need a periodic table, that would help in this case. Yes, lithium. Okay, Jonathan says lithium and fluorine, you're getting ahead of us. So this is lithium. Okay, and then what about the element on the right? You're good. You're fine, Jonathan. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if there's 9 electrons, there's 9 protons, and Jonathan was right. That's fluorine. Okay, so here's our 2 atoms, and we see the valence. Okay, remember these inner shell electrons, like the one I've pointed out, that's not a valence electron. The valence are just the ones on the outer shell. And everybody wants 8, or everybody wants a full inner or outer shell. So lithium here is very, very happy to give this 1 electron over to fluorine. And what happens to fluorine when it gets that 1 electron? Now we're going to have, we already have 7. This is 1, 2, 3, 4, 5, 6, 7 valence. And when it gets 1 more, this will become 8. And that's very, very stable. Okay, but what about lithium? Lithium doesn't have 8. When lithium's done, you have an atom now that looks like this. It's got 2 electrons, okay? This right here is the nucleus. That's not 8. Well, remember, the first energy shell is an anomaly. It's an exception. It's full when it has 2, okay? So lithium's still satisfied because the inner shell technically now is full. And the inner shell has become the outer shell, if you notice that. Okay, so that's just an example. That's what we're going to get into. When this happens, we create something called, well, we no longer have things that are electrically neutral, okay? We are going to create something called ions. And so that's what today's talk is going to be about. We're going to talk about ionic compounds, all right? When the electrons are traded, we make ions. So we're going to talk about why ions are important and what an ion is. So ion is obviously the root word of ionic. Okay, so an ionic compound is just a compound that's formed between 2 ions. And elements can very easily, some elements can very easily become ions and exist naturally, not naturally, but most of the time as ions. So I have 2 elements here that like to form ions, and they make an ionic compound. You guys know what this ionic compound is? Can anybody guess? Yeah, Matt said salt. Yep, this is sodium chloride. So you see the metal chunk of sodium. You actually saw this on the video last, was that last week? I forget what day. reacting with water. And then this is a vial or a tube of chlorine gas. All right, chlorine, and it's kind of green tinted. So if you're like, I think that looks green, you're right. And when you mix these things, okay, if this beaker is filled with gas and we put that hunk of sodium metal in here, when those things, when the sodium gives an electron to chlorine, it is such a favorable reaction. It's such a favorable thing that it gives off a lot of energy. And we view that energy as heat in this case, okay? Isn't that crazy? When you put those things together, you get like fire and smoke and all kinds of fun stuff. And then guess what? You make something that you can eat, okay? So that's the reaction between sodium chloride. And sometimes the trading of electrons is such a favorable thing that it gives off all this energy and you form a compound that's very stable, okay? All right, so we're gonna talk about ions. First off, why should we care about ions? Anybody know why ions are important? Why they're important to us? What do you guys think? Anybody know anything about ions? Summer said we need them for nutrients. Yes, we do. We eat them, okay? Electrolytes, yes, Bailey. Metals and non-metals, Tyler, what do you mean? Not saying you're wrong. There are metals and non-metals that form ions. But what's their significance? Why are they important? You guys are kind of getting at it. The first one, yeah, we'll talk about electrolytes. So anybody like Gatorade, different sports drinks? Okay. This is a very appropriate timing. RIP Kobe Bryant. This was very sad when I showed this slide last year. So my husband had a stomach bug this past weekend, and he goes, "Get me some Gatorade." Why do we do that? Why do we drink Gatorade? Or I don't know. Some people. My mom used to give me Sprite when our bodies are depleted or really exhausted. Why do we need things like Gatorade? Why does that help? Yeah, electrolytes gives us energy, rehydrates you. Yeah, so if your body's depleted of electrolytes, you experience things like what? Dehydration. Anybody been there before? It's terrible. Fatigue, exhaustion, you feel really weak or kind of shaky. You can feel nauseous. Anybody, when you get just depleted, you feel nauseous and kind of sick, okay? So these things help keep your body in a good state. And you can see, obviously, here, right here, electrolytes, and it tells you how much. We've got potassium, okay? There's other things too. If you really look close, we've got some magnesium, okay? One thing I noticed about Body Armor, I don't know if you know, Kobe Bryant, the reason I'm showing this, he had his own line of sports drinks called Body Armor. So compared to Gatorade, if you're interested to know, Body Armor had more potassium, less sodium, and half the amount of sugar. I was surprised by that one, half the amount of sugar. So Powerade too. Powerade decided to get sciencey on us and put the word in their drink label, okay? Powerade Ion 4. And that just was telling you what ions are in the drink: calcium, magnesium, sodium, potassium. So we drink these, right, to keep ions in our body. And just another name for ions is electrolytes. It's more of the health science related word, okay? They also have critical biological roles. All right, the reason we need them, the reason we take them in our diet is because of what they do for us. And I'm not going to read every word on this slide. You can kind of zoom in and read what each ion does. I want you to know the purpose of these ions. Okay, if I ask you on an exam, what is sodium important for? What is potassium important for? Give me 2 reasons or 3 reasons ions are important. But mainly they help with nerve transmission. So we have to fire, our nervous system is constantly firing, okay? And ions are important for that. They help regulate your body's water content. Okay, they're important for that. You'll read that on several. Osmotic pressure, regulate osmotic pressure, okay? And then muscle contraction. A lot of them are involved with your muscles contracting, okay? One thing I thought was unique is magnesium is important for activating enzymes. What is an enzyme? What does an enzyme do?
It speeds up reactions, right?
Yes, it is a catalyst. I like that word, Kendall. Okay, in the chat. It helps with breakdown, Bianca. Okay, so the enzymes are proteins that help make reactions go faster because our body needs to get things done in a certain time. So magnesium, an ion, is important for activating enzymes. Calcium, we know, helps with bone and teeth formation. And then chlorine is also important in stomach acid, right? We have HCl in our stomachs to help break down food. So they're important in digestion as well. Another reason they're important, what do we have here? Red blood cell. And specifically, I'm showing you what's called a heme group. Okay, what ion do you see in this heme group? Where's the ion? Okay, I'm gonna go white. I think white will show up better than black. Right here. Fe+2. Okay, iron. It's a metal that is an ion in this case, a +2 ion, and we could not bind oxygen without iron. Okay, iron is part of the heme group. It's why red blood cells are red. Iron's, probably some of you know that iron is a high content in like red meats. But we cannot bind oxygen. Okay, why does your body need oxygen? What does oxygen do for us? You're like, I don't know. I just know my cells need it. Oh, could I go back up for a second? Yes, I can. I'm going to keep talking about oxygen though. Okay, what would not happen? The main thing that would not happen if you did not breathe oxygen is that your body could not make ATP. Anybody heard of ATP before? That's critical, right? It's your body's energy molecule. Yep. So you breathe oxygen so that you can make ATP. Okay, they're directly kind of coupled or linked. And iron is critical for that. If we don't have iron, we can't bind oxygen. So there's another role for ions, biological role. Another thing, hopefully you all brushed your teeth this morning. Anybody left the house before and you're like, oh my gosh, I did not brush my teeth. Yeah, you feel like everybody immediately knows. Look, in toothpaste, if you zoom in, I know this is blurry. This hurts my eyes to look at it. You got potassium nitrate is another polyatomic ion. Okay, do not forget your polyatomic ions for exam 1. I could totally question you on those 11 that I asked you to memorize. So know those 11, know the formula, know the name. Sodium fluoride, okay, this is Na plus and F minus. These are ions that are in toothpaste, okay? So they're in a lot of different commercial products that we use. Here's just an example of one. All right, so that's several reasons they're important and not even all the reasons, just a few. But now that we've talked about why they're important, what is an ion? Okay, well, it is an atom that has either lost or gained, an atom that has either lost or gained a valence electron. So again, we're just talking about the outer shell, electrons in or out of the outer shell, and is therefore no longer electrically neutral. Okay, no longer electrically neutral. What does that mean, electrically neutral? Remember, like what we said earlier at the beginning of this lecture, all atoms before any electrons are lost or gained they have the same number of protons and electrons. Okay, so if you have, like we said with lithium, this one was lithium, this one's fluorine, 3 protons, which are plus charge, and 3 electrons before anything is given away or received. So that adds up to 0. That's what we mean by electrically neutral. The number of negative charges balance the number of positive charges. Fluorine, 9 plus charges, 9 protons, and 9 electrons, 9 minus charges. That adds up to 0. Okay, so all atoms start out neutral. Now, let's walk through what's happening with lithium. It is losing, it's giving away an electron. And when it does so, what happens to that charge balance? Well, it changes. We still have 3 plus charges, 3 protons, but now we only have 2 electrons. Okay, so the charge balance with that, a +3 and a -2, that adds up to a +1. That's what we call a cation. Okay, maybe you've heard this word before, but a cation overall has a positive charge because it has lost electrons, all right? Loss of electrons always leads to a cation, because now there's an imbalance. You have more protons in the atom than you do electrons. Okay, what if we gain electrons? What if we're fluorine? Okay, and we get that 1 electron that lithium's giving away. Now we have 9 plus charges and 10 electrons, 10 minus charges. So that adds up to a -1, right? If we're fluorine. And this is what happens when you gain an electron, you become an anion. So we call anything that gains electron an anion. Overall, the charge is negative. And here's the deal. Atoms can give away 1 electron. They could give away 2 electrons. They could receive 1 electron. It's more than 1, okay? Sometimes it's just 1. Sometimes it could be more than 1. Sometimes they could give or receive 3 electrons. So think about how the charge would change if an atom received 2 electrons instead of 1. It would be a -2 charge overall. If an atom gives away 3 electrons, it would be a +3 charge overall, okay? But it all has to do with this simple kind of math that we're doing right here, the number of protons and electrons in the atom. This right here is key, okay? For everything we're leading up to, if you can do this, this is key to know how to predict the charges on ions, all right? So here's an example. I want you to ignore this stuff over here, all right? We've got sodium, okay? A sodium atom. And we can see the nucleus. There's 11 protons in the nucleus. And then we see the energy shells, right? First shell, second shell, third shell. And these numbers over here that I'm boxing in, these are the number of electrons in each shell. So if you add all of that up, you have 11 electrons, which we know because it's a neutral atom, right? Starting out, it's neutral. No charge. But we know sodium's going to lose 1 electron, okay? Because it is in main group what? Sodium is in main group. What main group is sodium in? The alkali metals. The alkali metals are main group 1. Thank you. So it's got, there it is, the 1 valence. So when it loses that, guess what happens? Couple of things happen. First off, that third shell just completely goes away. Now we only have 2 outer shells. We don't have any electrons in the third shell, so we don't have a third shell. And we still have 11 protons. That has not changed, and that will never change. But now we have 10 electrons because we lost 1. And so overall, now we have a cation. Sodium is positively charged. And to indicate that, we always write the symbol for the element, and then we put the charge that that atom or that element now has. So it's a +1. You can write plus, or you can write Na +1. They both mean the same thing. I think just writing the plus is easier here. If it has a +2 or a +3, you need to write the number, okay? So questions on what we just discussed. What do you notice too? As you become a cation, because we don't have 3 shells now, the atom itself or the ion is smaller. The cation is smaller than the original atom. So cations are smaller than charge neutral atoms. Okay? So that's a minor thing, but it's important to know. Size changes. Okay, let's go to, everybody good there? I don't want to move too fast. Okay, let's go to, we know that sodium likes to react with chlorine. Okay, so let's look at chlorine. See the same 3 energy shells? Chlorine has 17 protons in the nucleus, and across those 3 energy shells, the atoms are distributed. Remember, it can only hold 2 in the first shell. The second shell has a full 8, and then we've got 7 valence. So what does chlorine really want to do? It wants to get 1 more. And again, starting out, the atom is neutral. 17 plus charges and 17 minus charges adds up to 0. And when it gains 1 electron from, say, somebody like sodium, who's happy to give 1 away, now it's going to be added to that third shell. Okay, now we have 8 in the outer shell. The number of protons, again, does not change, but now we have 18 electrons. So we have a +17 and a -18. That adds up to -1 overall. Okay, you can literally add these up. 2 + 8 + 8, there's your 18. So to indicate this is now an anion because it gained an electron, you have chlorine and you indicate the minus charge. If it's a -1, all you have to do is write the minus. But if it's like a -2 or a -3, again, you need to write the number -2 or -3 as the charge. Okay. All right. Questions on what we just covered? We're going to pause on this. I want to talk about 2 properties really quick. Ionization energy and electron affinity. These are properties that help us predict how easily or how difficult it may be for an atom to give up an electron or receive an electron. Sorry, I have a question in the chat. Could hydrogen share with anyone to get electrons or lose electrons? What do you think hydrogen's going to want to do? Does hydrogen want to gain an electron or give one up? This is kind of a hard question because hydrogen, well, one proton and you got something with one electron, okay? Hydrogen's going to follow what the other main group 1 elements do. It's going to tend to give that electron away, okay? So oftentimes you'll see hydrogen forming something with a +1 charge. Hydrogen ion. This is what hydrogen typically does, okay? So it doesn't gain, even though you think, well, it wants a full outer shell. Again, hydrogen is such an anomaly in so many ways. It's grouped with the metals, but it's a non-metal. It likes to give an electron away instead of receive another one. So it behaves like the group 1s in that way. All group 1s like to give a proton away or an electron away, sorry. Yep. Great question. And then somebody asked in the morning lecture, somebody said, can those electrons be given to multiple atoms? Let's say we have calcium. Calcium is in main group 2. If you're looking at a periodic table, calcium is in main group 2. So how many valence does calcium have? 2 valence electrons. And sure, calcium could make 2 bonds, 2 ionic bonds with fluorines. Fluorine only wants to receive 1 electron. Calcium has 2 to give. So once one particular fluorine atom comes along and it gets that 1 electron from Coin, it says, I can't accept anymore. So Coin has to find somebody else to give the other one to. Okay, so it could give 1 electron to this fluorine atom. It could give another electron to this fluorine atom. Does that make sense? Sometimes they could be distributed different ways. Think about what could happen if you have a metal that wants to give away 3 electrons, like aluminum. Aluminum could do that. It could make bonds with 3, for example, chlorine atoms. Okay, so it's giving 1 electron to each of these chlorine atoms. Okay, so they can definitely be distributed different ways. Okay, ionization energy. What is this? So because some elements want to give away electrons, that's a very favorable thing for them to do. And some atoms really don't want to give away an electron. They want to receive an electron. We have this property called ionization energy, and it's the amount of energy that is, required for an atom to lose a valence electron, okay? So there's energy associated with these processes. When I showed you the reaction between sodium and chlorine earlier, and I said the trading of that electron from sodium to chlorine is so favorable that it gives off heat, which is why you saw that hunk of metal burning. It's because energy is associated with these things, all right? So when we have to pay some atoms or all atoms a certain amount of energy to lose an electron. Anybody ever had to pay a pet deposit before? You got a pet, you want to move into your apartment, and they're going to charge you some money to keep your pet there. Okay, it's kind of like this. We have to pay that atom some energy to get what we want, for it to give away an electron. And in doing so, you're going to form the cation and that lone electron that can then go to another atom that's happy to receive it. But there's a certain amount of energy required, okay? So keep that in mind. Ionization energy is how much energy, there's a threshold of energy, and it's different for every atom, that we have to pay it to give up the electron. All right, electron affinity is kind of the opposite. It's the amount of energy released when an atom gains a valence electron. Okay, so again, some atoms, think about the word affinity, by the way. What does that mean? If I tell you I have a high affinity for ice cream, which is very, very, very true, that means I like ice cream a lot, okay? Certain elements really like electrons, and they want to bind, they want to gain another electron. And because that's so favorable for them, they're just going to release energy, and they're going to be more stable once they get that electron, okay? So the way this looks, if you write out a reaction for an atom plus an electron, so they're gaining an electron in this case, is going to give you the anion, it's going to release energy, all right? It's very favorable. They're more stable after they release some energy. All right, I'm going to look at this graph. We're going to draw trends, okay? Remember how we drew a trend for atomic radius? We're going to draw trends for ionization energy and electron affinity. We're going to do that using this data. So in the red is the ionization energy. Okay, in the red. So let's look at the red set of data. So notice again, remember the word periodicity that we talked about, systematic trends. I see some trends here. I see some spikes. What elements, I'm going to underline them, are at the peak of this data? Anytime it has a spike, what element's at the top? I think you're going to notice something. What kind of elements are these? He, Ne, argon, Ar. Yeah, noble gases. Somebody just said Nobel gases, noble gases, okay? So the noble gases have the highest I'm going to abbreviate, ionization energies. Okay, why? Can anybody think of why?
Because they don't like to react with anything.
Yeah, they don't want to give away an electron. Why don't they want to give away an electron? Thank you, Kai. They already have 8. Okay, they're where they want to be already. So because they're already stable, that makes sense that the threshold of energy we would have to pay them would be the highest. We got to pay them the highest deposit of energy for them to give an electron away. Okay, it can be done, but they're going to make us really pay for it. All right, so they don't like to. But what do you notice at the bottom? What elements have the lowest ionization energies? Thank you, Allie. Group 1. Okay, all the alkali metals, they got 1 valence. They're more than happy to give that electron away. So they're like, you don't got to pay me hardly nothing. I'm going to give that electron away. So the alkali metals have the lowest, double arrow down, ionization energies. Okay. All right, so where are the alkali metals? Where are the noble gases? We're going to draw the trend now. I think we have enough information to start drawing this. Here's my periodic table. Again, please hold your applause. Noble gases are where? They're over here, right? And the alkali metals are group 1. So we've got a group on the extreme far left and the group on the extreme far right. If we're drawing an arrow horizontally as you go across from right to left to right, what happens to ionization energy? Increases or decreases? Increases, yes. Okay. Now let's finish the trend. If we go down the periodic table, let's talk about this one. Fill in the blank in a second. Let's go back to the graph. Before we can fill this one in, I'm going to erase a little bit so we can see. Let's look at like the group 1s. This trend is not as obvious, so we got to look a little closer. Okay, here's lithium. It's right on the line, this gray line. The ionization for energy, sodium right on the line. But what do you know about potassium? Potassium's below the line, and I'm talking about this line. So as you go down group 1, because it's lithium and then it's sodium and then it's potassium. As you go down group 1, ionization energy eventually decreases. Do you guys see that? Okay, so this kind of goes down eventually. All right, but it's not as obvious, but there is a trend. Okay, so that's the trend for ionization energy. All right, let's talk about electron affinity. That's the one in blue, the data in blue. So I'm gonna erase so we can see. You can keep your notes there, but I'm gonna erase just so we can look at the blue data. Okay, what do you notice? There's some spikes in the blue data, F, Cl, Br. What elements are these? What elements, in other words, have the highest affinity or desire for electrons? Thank you, Claire. These are the halogens. Okay, and they are right here next to noble gases. They're the wannabe noble gases. So if we're drawing a trend in electron affinity, as you go towards the halogens, I'm going to abbreviate again. Electron affinity increases. Okay, the graph goes up. Okay, and we don't have any other elements labeled here, so we don't have a lot of evidence, at least from this graph, on the other part of the trend. But as you go down, I could draw it on the other side as well. I have some more space over here though. But as you go down, what happens to electron affinity? It decreases, okay? So those are the trends in electron affinity. Essentially, as you go towards fluorine, I'm gonna draw fluorine in here. Zoom in. Fluorine is the top halogen. I'm gonna circle fluorine. Fluorine is the single element that has the highest electron affinity, okay? So as you move towards fluorine on the periodic table, you have a higher and a higher and a higher draw for electrons, a higher electron affinity, okay? As you move away from fluorine, your electron affinity decreases, okay? Questions on that? We're gonna do a poll question. I wanna see how well that lands with you guys. So I'm gonna launch this poll. It's on ionization, a trend in ionization energy. I want you to list the following elements in order of increasing ionization energy. So you're gonna need a periodic table and not the one I've drawn. Here, do I have one? Do I have one down here? Here's one. If you wanna look at my screen. So find those elements. You're going to order them in increasing ionization energy. So start with the element that has the lowest ionization energy, end with the element that has the highest ionization energy. All right, I'm going to give you about 30 more seconds. All right, go ahead and get your answers in. We're 92% voted. I'm going to end the poll. Okay, by and large, share results. By and large, the most popular answer, if you can see that, 65% of you guys picked the third choice, which had cesium, then potassium, then iron and oxygen. But the other choices were also picked by a few people. So let's talk about this. Maybe somebody who picked the third choice. Why did you pick it? Why did you order them the way you did?
Because cesium was at the bottom, so like to me that was like the least iron. What's it called? Iron.
Ionization energy.
Yeah, that. And then potassium was above it, so that means it had more. And then when you go to the right, you find iron, and then oxygen was furthest to the right.
So if we're gonna circle these, I'm gonna make this a little bit thicker. Here is cesium, right? Here was potassium is above it. Then you go over to the right, there's iron, and then there's oxygen, okay? So remember, ionization energy, as you go down, it decreases, which means as you go up, it increases. So because, like Kishan said, potassium is above cesium, it has a higher ionization energy. So you want to pick an option that has cesium before potassium. And that leaves you with options 3 and 4. Okay. Then as you go from left to right, ionization energy increases. So iron has a higher ionization energy than potassium. And then if you keep going right, oxygen, you eventually get to oxygen. So it has the highest. Okay. That means we would have to pay oxygen a lot of energy for it to give away an electron. Oxygen doesn't want to give away an electron, it wants to gain 2 electrons, right? It's got 6 valence, it wants to gain 2. Okay, cesium's like, you don't got to pay me nothing, and I'll give an electron up really easy. Okay. All right, good. So it seems like if you struggle with that question, it's okay. Just make sure you kind of review this and let me know if you have any confusions on this stuff. Okay. Let's go back up. So those are our trends. I want you to know that the 3 trends: atomic radius, electron affinity, and ionization energy. I want you to be able to answer questions just like that, what we just did on the exam, okay? If I pose those on the exam. Okay, forming ions. So I told you we'd eventually get to a rule that talked about magic number 8, and that's going to be the octet rule. So we're going to fill that in a second, but remember these electron dot symbols or electron dot structures. This is just an example of a reaction for us to predict. If I didn't show you your products yet, if I just had these reactants and I said, okay, how are these going to react? What products are you going to get? How are electrons going to be given or traded? Based on the number of valence that you can quickly see, you should be able to write the products, okay? We know sodium is going to give away 1 valence. Chlorine is an example of an atom who has 7 and wants to gain 1. So this lone electron is going to go over to chlorine. And in doing so, here's their new structures. Now, somebody asked in the first class, they said, well, what if you draw sodium as having a full shell beneath? Because it does, right? That's what we saw earlier. If you had, now we say sodium technically does have 8 on the shell underneath, and that second shell became the outer shell. So if you drew this and you wrote that, I would not count you wrong. But it's very much more common to draw group 1 and 2 elements like this, with technically no valence because they've given their valence away. Okay. So we draw sodium with a plus, and then you draw chlorine with all 8, and then you got to write in the minus charge as well to be complete. And our ability to know what's going to happen and to predict what whether elements are going to give away or receive electrons, and then also predict what kind of charge they're going to have, that is made possible by the octet rule, which says that main group elements, so that's not all elements. You know how to count main groups. That's only the main group elements undergo reactions that leave them with 8 valence electrons. So here's what I want you to know what the octet rule says for exam 1, and I want you to know the significance of it. Okay, what does it allow us to do? It allows us to predict whether atoms will give away or receive electrons, and it allows us to predict what kind of charge those ions will then have because of that. This is just for the main groups. So you guys tell me, and this is definitely incorrect. Should be like this. But you still get the gist. We have element X has 2 valence. Element Y, you can count the dots. There's 6. What products would you get? Can you repeat what it allows us to predict again, please? Yes, McKinsey. It allows us to predict if an element is going to give away or receive electrons. So what it's going to do. And it allows us to predict what charge that element would have as an ion for the main group atoms or elements. Okay, Kendall says that we're going to get X plus and Y minus. And I know you can't draw the dots in. How many dots, how many electrons should I give? Cheyenne says Y minus 2. What do y'all think? Is Is it y minus 2? Hunter says x plus 2, y minus 2. Summer says x plus 2. Okay, plus 2, minus 2. All right, should we draw any dots around any of these? Yes, no, maybe? Well, once y accepts, yeah, around the y. Okay, good, I'm seeing it. Yep, all right, this is what you should have. So x is going to give away both of those valence. Y is going to accept both. And this is what you'll get in the end. X is going to have a plus 2 charge left over. Y is going to have a minus 2 charge. Anybody confused on that? Like why x has a plus 2 and why y has a minus 2?
Yes. So why does the x have a plus 2?
Okay, I'm going to open the floor. Does anybody else maybe want to tackle that question before I do?
Because X gave away 2 electrons, so it's becoming more positive. So it gets 2 plus instead of a negative.
Yeah. Yes, thank you. So we don't know. I didn't tell you what elements these are. So I'm going to make up a number. Let's pretend that X has 10 protons, which means 10 plus charges. And starting out, before it gives anything away, that means it also has 10 electrons, 10 minus charges. So now on the product side, after it gives away 2, it still has 10 protons. Okay, remember, these are just made up numbers. And now it only has 8 negative charges because it gave 2 electrons away. Okay, 8 minuses. So that means you would have a plus 2 overall. The sum of those is plus 2. Y has a minus 2 because, I don't know, let's say it has 20 protons, 20 plus charges, and 20 electrons. I'm just making numbers up. Well, when it receives 2, now over here it'll have 20 plus charges and 22 negative charges. Okay, so that would mean it has a minus 2 overall. All right. Which direction does AE switch those? EA, electron affinity, increase again? I'll go right back up, right here. It increases left to right. And as you go up. Okay, as you move towards fluorine. Okay, you guys tell me. There's another kind of practice problem. I don't have a poll question for this, but I'd love to know. You can type it in the chat. What element is this? And is it just an atom? Is it an ion? Does it have a charge? If so, what is that?
Can you say that one more time?
What element is this portrayed with this picture on the slide? And is it an ion or is it a neutral element? If it is an ion, does it have a charge? Okay, so I'm seeing in the chat, a lot of people are saying oxygen with a minus 2 charge. It's an anion. Okay, how do you know it's oxygen? Eight protons, perfect. Okay, remember that's the identity of an atom. So 8 protons, you would go right up here to, well, it's right below actually. To oxygen, and you can see oxygen has a little 8, right? Right there. Tells you the number of protons. Okay, so that's how we knew it was oxygen. So it's oxygen, and 8 protons means 8 plus charges, 10 electrons means 10 minus charges. So positive 8 minus 10 equals negative 2. It's received 2 electrons, so the full shell, outer shell is full now. And so it's oxygen with a minus 2. Good. All right, questions so far on how we're figuring all of this? So based on what we've talked about, there's like 4 or 5 groups, main groups on the periodic table that are very, very, very predictable when it comes to ions. And here's what I mean. You can always predict certain groups that they're going to be either cations or anions and what charge they're going to have. Let's look at those. Group 1A and 2A. These are 2 groups. Any element in these groups are always predictable. Okay, these are metals. I don't know if anybody's heard me say, I think I've said it. Metals always form cations, right? So here's the example of their electron dot symbols. And again, I'd want you to do, okay, one on each side, but whatever. You get the point. There's their valence. They are always going to give their valence away. Okay, so they give electrons away. Because of that, they're always going to form cations. Main group 1. So what I mean is these metals right here, anything in main group 1, they'll always be a +1 charge when they're done. Main group 2, that's the calcium and the magnesium, they'll always be a +2 charge. All right, so what I like to do, if I have a periodic table handy, I always go in and I write in, these are +1 elements, these are +2. And that's easy because it matches the main group numbering. All right, let's look at the next groups that are pretty predictable. Group 6, where's group 6? It's right here. These are always predictable. Why are they predictable? They have 6 valence electrons. Remember, the valence numbering matches the main group numbering. So their main group 6, 6 valence. They want to have 8, right? So they want to gain 2. So we're going to give them, when they get 2 electrons, now they have a full outer shell. You see all 8 dots around the oxygen and sulfur. These are just examples of main group 6 elements. And then we write the charge in, -2, -2. Always predictable. So I would write a -2 over these to help myself remember. This is what kind of an ion they're going to form. Anions with a -2 charge. The charge here doesn't match the main group numbering. That was just for groups 1 and 2, okay? Now on the right side of the periodic table, we're talking about anions. So these have minus charges. And then the next group that's very predictable is group 7, the halogens. Okay, so these always form anions with a -1 charge. They have 7 valence. So they just want to get one more. So when they get 1 electron, so I'm talking about fluorine, chlorine, bromine, iodine, those are our halogens. What they look like after that is they've got a full set of 8 dots around them, and they have a -1 charge. Now there's a couple of main groups we haven't talked about. We've talked about 1, 2, 6, and 7. Why have we not talked about 8? And we're not going to talk about 8. It's already full. They don't want to give away. They don't form ions, okay? Good. I'm going to launch another poll question because there's another group we haven't talked about. And I want to see if you can kind of predict what would happen. Okay? We have not talked about main group 5, but based on what we have talked about, what do you think? How would main group 5 follow the pattern here? Element X is in main group 5. What kind of ion would it form? It should be predictable as well. All right, I'm gonna give you 10 more seconds. We're almost there. What kind of ion do you think it would form? Okay, we're 90% voted. Get them in, get them in, get them in. 5, 4, 3, 2, 1. I'm gonna end it. All right. So, by a landslide, most people said an anion with a -3 charge, okay? But a few people said different. So let's make sure this is the right track here. If you're main group 5, let's just zoom in on these really quick. Here's main group 5, okay? The first element there is nitrogen. The second one is phosphorus. Okay, it doesn't matter which one we're talking about. Any element in main group 5's got 5 valence. Okay, so somebody who picked that it would be an anion with a -3 charge. Why'd you say that? Anybody? Tyler in the chat says wants to receive. They're going to receive. Okay, so if we've got 5 valence, the shortest route here, and we want 8, we're trying to get to 8, is +3. +3 what? +3 electrons. Okay, so we're adding 3 negative charges. I know the plus sign probably freaks some people out, but we're adding negative charges. Remember, electrons carry negative charge. So if we're giving something 3 more electrons, that means overall we're going to have a -3. So it's going to be an anion because anions carry negative charges. They gain electrons with -3 charge. Yeah, it doesn't want to give away 5. That's the long route. Nobody likes to go the long route. They always like the shortest route, okay? All right, what about main group 3? You can see here, aluminum. Anything in main group 3? Well, actually, I shouldn't say anything. Typically just aluminum. We're going to give away 3 electrons, form a cation with a +3 charge. Okay, very quickly here, we have little time left. We're going to talk about transition metals. We have yet to talk about transition metals. And there was a question in the chat. Keegan said, if we want to, are we allowed to print off a periodic table to help us with the exam? I will always provide what I call a resources page, okay? And it will have a picture of a periodic table, and that periodic table will look just like this one, okay? Except for it won't have my handwriting on it. And here's why I like this one. You can see the name of the element very clearly. Some of them, they're blurry, but this one is clear enough for you to read it, and you can see the symbol, okay? So I really like this periodic table. So I'll provide that on Blackboard. I'll create a new folder called exams, and it'll be in that folder when you go to take your exam. You can print that off, have it, look at it for sure. All right, transition metals down here. All right, so here's the transition metals. How many valence do transition metals have? Anybody remember? We said they all have, thank you, Bradley, thank you, Keegan, 2 valence. But looking at this, okay, look at this row right here. We just show one row of the transition metals. There's more than this, but we're just showing you an example. What do you notice? Anybody notice anything? Anybody kind of see something makes your head turn a little sideways? What do y'all think? Anything unusual? All positive charges. Okay, great observation, Allie. Tyler and Samantha, they say different charges. Yeah, okay. Both of those observations are important. Let's talk about those. They're all positively charged. So transition metals will always form cations. They will always give away electrons, okay? They will always lose their valence electrons first, okay? And sometimes they will then lose additional electrons, okay? So they don't fit the mold. They don't obey our rules all the time. They obey the rules in the sense that they're going to give away their valence, but sometimes they can give away more than their valence. And that's where you get certain transition metals that can carry different charges. Like what you see here with chromium. It can be a +2 or a +3. Iron, a +2 or a +3. So that's the second point down here. Transition metals can therefore sometimes form multiple ions with unique charges, different charges. So here's a table that gives you some examples. And there's a couple of things I want to point out before we finish up. You see certain transition metals in red, okay, these, and you see certain transition metals in blue. And there's a lot of blank squares. Those are transition metals too, but I'm just pointing out a few examples here. In red are common ions with more than one possible charge. Cobalt, CO, can be a +3 or +2. Copper, Cu, can be a +2 or a +1. Okay, other metals like silver, Ag, is just a +1. So here's the deal. If I just wrote the copper ion, okay, copper is a transition metal that can be a +2 or a +1. If I just write the copper ion, how do you know which one I'm talking about? Do I mean copper +2, copper +1? We have to have a way of differentiating. And what we do is we use Roman numerals. So we would say the copper 2 ion, or we would say the copper 1 ion. So if you have a transition metal, like you see here on this slide, and this will tell you which ones can form more than one charge, you need to put Roman numerals when you name that ion. And on next Tuesday, we're going to talk through so many rules, and that's all we're going to do pretty much is learn how to name formulas and ions and things like that. So that's a rule for transition metal with multiple charges. By the way, some of you may have noticed down here we have mercury. Mercury's just a weird guy. I just want to point this out. It's not a typo. It's just that we have 2 mercury atoms here, and each one has a +1 charge. Okay, so in case you're wondering that, we call it the mercury 1 ion. All right. Now in blue, the ones in blue, these are the ones that invariably have 1 charge. Okay, they form a particular cation with 1 charge. So there's no questioning. All right. So if I just write the silver ion, you know what I mean, because there's only 1 silver cation. It's a +1. So you can, it's okay to omit Roman numerals. Now, you're probably like, gosh, I don't know when to omit them. I don't know when to include them. Well, that's why you have this slide, okay? But if you were to write the silver 1 ion, I'm not going to take off points, okay? It's a little redundant when you know better, but it's okay in this case. Now, if you forget Roman numerals when you should have them, I will take off points. Questions on transition metals?
Can you explain like the like when you include them again? Like
Yes. Anybody want to jump in on that before I just, when do you include Roman numerals? That's the question.
If they have more than one possible charge. So for example, copper Cu can be a +2 or a +1 charge.
Okay, so these squares that have like the 2 options, you got to put Roman numerals. So Olivia said, I love this. There's always people that are like, so let's just simplify this. Is it just better to always put the Roman numeral? You know what? That is a safeguard, okay? I'm not going to count you wrong if you have a Roman numeral. Now, do you put Roman numeral for main group metals? These are metals, but they're not transition metals. And the answer, thank you, Bradley, thank you, Matt. No, do not put transition or Roman numerals for those transition, or sorry, do not put Roman numerals for the main group metals. They're only for transition metals, okay? Specifically for transition metals that can carry different charges. Does that help, Kishan?
How do you know which one is like 1 and which one is 2?
It's Keegan, it's not that certain iron atoms form a +2 and certain iron atoms form a +1. It's that any iron atom could form a +3 or a +2, depending on what they're interacting with. Does that help? I don't know if that answers your question.
I mean, like the Roman numeral.
Oh, right here?
Yeah.
So if you put 2 slashes, that's a 2, then a 1, like this is a 1, this would be a 2. This right here is a 3, right? How do you do a 4? Like that. And a 5. Okay. So that's Roman numerals. Does that help, Keegan? Kiara says, can you scroll up? Yes. Is that what you needed? Okay. Let's go down. We got one more little practice slide. So I want you to do A, B, and C here. Write the symbol for the ion. When you write a symbol, you write the elemental symbol. Okay, and I've got those right here for you if you don't have a periodic table handy. And then you need to write the charge if it's an ion. Can you repeat the question? Right here, Bradley, on the slide. Just write the symbol for the ions formed in the following processes. So for A, you've got a gain of 2 electrons by selenium, Se. So we're going to write Se. What should I write for the charge? Is it a +2 or a -2? Yes, -2. Don't be confused by the word gain. Electrons carry negative charge. So if you're giving something 2 electrons, you're increasing the amount of negative charge. Okay, a loss of 2 electrons by barium. Things that give away electrons, thank you, Kamaya, should be a +2. Okay, a gain of 1 electron by bromine. Br. You gain 1 electron, you have a, yes, -1. So, how do y'all feel with this today? I'm going to launch that poll that I did again the other day. I just want to know how many of you feel like you got a decent amount, all of it? You're like, I'm so confused. Feel pretty good with this. This is as far as I wanted to get today, but I'd love to know how y'all feel. Ions are important. What we're learning today is going to travel with us for the rest of the semester, okay? So if you are lost on valence electrons and ions, please, this weekend, you have a whole beautiful weekend ahead of you, okay? I know, again, some of you work, some of you are parents, some of you have busy schedules, but please, please make time to review this stuff, or you guys can set up, I'm all for, as the exam gets closer, set up study sessions via the group me. Can y'all set up Zooms as students yourselves? I'm gonna end the poll, by the way. So most people said they got a decent amount, all right? That's good. But don't hesitate to set up Zooms and study together. Send me questions. I've got office hours. Hardly nobody came to my office hours today. But I'm available next Tuesday from 9:30 to 10:30 especially, or by appointment. And I'm happy to answer questions. So, but essentially, if anybody has any right now, I'll stick around for a couple minutes and answer those.
Could you go over like, okay, why would like copper be like 1 or 2? Like, I don't get that.
Yes, I can. Before I do that, if you got to head out, that's all for today. So thanks for joining. But why could copper be a +1 or a +2? Why could iron be a +3 or a +2? Hold on, Grace. I'll get to that in a second on the chat. So basically, it goes back to if you look at the slide that has all the red text and we filled in the blanks. It says transition metals will always lose their valence electrons first. Okay, you see that slide? I know I'm not sharing my screen right now, but you should have the notes. All transition metals have 2 valence electrons. So when they lose those 2, they carry a +2 charge. Okay, except for you're probably realizing there's lots of exceptions in chemistry. Silver will only lose 1 valence electron, and there's a reason for that, but we don't have to go into it in this course at least. So usually they form a metal with a +2 charge. Sometimes copper, for example, or iron, let's go with iron. Sometimes iron will lose an additional electron depending on what other elements it may be around, okay? And it could be a +3 charge, okay? So it's just the fact that they may lose an additional electron. And as far as why that happens, again, that really gets into the electronics of atoms. And we're just not going to go that deep in this course. So I'm sorry for that. But that's what happens, at least. Does that help, Kishan?
Okay, so like say if okay, let's say iron lost like 3 electrons. Would it be if like Fe3 or like +3 and then the Roman numeral 3?
Oh, you're asking it right. Let me share my screen. No, so let me make that distinction. This is a great question.
Yeah, that's what I was trying to ask. I didn't know how to
Okay.
word it.
Okay, I'm sorry, Keegan. So when you're writing the symbol, I'm going to use the word symbol for the ion. You just write the elemental symbol Fe, and then you write +3. Okay. If you're writing the name of the ion, then you're going to write iron 3 ion. Okay. Now, we're going to look at compounds on Tuesday. So like what happens when iron joins up with fluorine? What could happen? Okay. So for example, if you have iron, fluorine, iron fluoride, okay? And again, we're going to get to all this on Tuesday. And I say, name that compound, write the name of it. That is when you would use this. You would say, this is iron 3 fluoride. Okay. So that's when writing out the Roman numerals would be important. But if I just like down here, when we were working these problems, if I just say name the ion or write the symbol for the ion, if I say write the symbol, you're just writing the elemental symbol and you're writing the charge. If I say write the full name of the ion, that's when you would write, I don't think selenium is a transition metal. But if I said write the name of the copper 2 ion, okay, then you'd write copper, you would write the Roman numerals, okay, copper 2 ion, okay. So if I tell you write the full name, you write it out with the Roman numerals. If I say write the symbol, you just write it with the elemental symbol and the charge. Does that help?